All right. Good afternoon, everyone. Let's start. So first of all, don't forget today is the deadline for our homework 3. I think from the office hours, I found like a lot of students have finished that. But if you haven't done that, just don't forget to submit the homework by today. Otherwise, you might get some penalty. And then we'll release our homework 4 on Thursday. And homework 4 will ask you to do some numerical experiments with variational inference. So there is a big bonus point, like 100 bonus point, which is actually has the same amount of like regular total number of points for the homework. If you would like to implement the variational inference for LDA, the latent directional allocation model we discussed in the last lecture as your practice, as a real practice of variational inference. Don't want to do that, that's fine. It's up to you. Right. So yeah, this model, yeah. And we have in the homework link, you'll see some kind of a standard benchmark data set for latent directional allocation. It's actually a well pre-processed a collection of the document. It's just the news articles. And they do some polar stemming. They just remove those like semi columns and columns and those kind of things, and leaving just the words. And you can implement your latent directional allocation model and run it and see what kind of topics can you extract from this set of documents. It'll be fun. It'll be fun. And if you're interested in doing that, you have enough time and energy doing that, go ahead, try that. If you're not willing to do that, that's fine. That's bonus question. Okay, so through the last lecture, we actually have wrapped up variational inference, right? We use this latent directional allocation model as an example. But here I just want to give a quick summary again for the variational inference, right? Variational inference essentially to leverage the framework. It's called a variational view, right? Your computation of the true posterior inference, like X is the, maybe I should use Z. So this is your model, this is your data, right? So the following Bayesian rule, your computation of the posterior is to divide the joint distribution of your latent random variable and observe data by the marginal distribution of data, right? So this formula is very simple, it's very elegant, but it's really tricky to compute. The reason is that the denominator, which is the marginal distribution of data, involves a integral over the joint distribution, right? And due to a complicated form of the joint distribution, which is often in practice, this integral in most cases are not analytically tractable, meaning that I don't have any closed form, right? So how do we address this problem, right? Variational inference try to use another view to look at the computation of the posterior distribution. That is the variational view. Variational view comes from the observation that the log marginal probability, sometimes people call it log evidence, can be written as a expectation of any valid distribution over Z, and take expectation over this log fraction. That is the ratio between the joint distribution. Sorry, it shouldn't be X, Z. The log ratio between the joint distribution and your introduced Q of Z, then plus let's take expression of this, plus the KL divergence between your introduced distribution Z and the true posterior distribution, right? You can obtain this by applying the Jensen's inequality, which emphasized quite a few times. That means if you don't make any restriction over Q of Z, if you just maximize this guy, which we often refer to as elbow evidence lower bound. Why it's lower bound? Because the scale divergence is always non-negative, so the log evidence is always no less than the evidence lower bound. So since the evidence lower bound is fixed, so maximizing this evidence lower bound is equivalent to minimizing the scale divergence. If you don't put any constraint over Q of Z, means that theoretically, if you assume that you can always find the best Q of Z, which maximizes this elbow, then you guarantee that your optimal Q of Z will be the true posterior distribution. Right? Why? Because when it reaches maximum, that means this guy and this guy is equal, and that means the Q divergence becomes zero. Q divergence is zero if and only if Q of Z is exactly the same of the true posterior distribution. Right? This is called a variational view of the Bayesian inference, meaning that the computation of the true posterior can be equivalently considered as an optimization problem. Right? You actually optimize this evidence lower bound with respect to arbitrary distribution Q of Z. Right? If you're powerful enough, you can obtain a true posterior through this optimal Q of Z. However, this is usually infeasible as well. So the variational inference is trying to simplify this optimization problem. So I maximize this elbow. I maximize this elbow. If I don't put any constraint over Q of Z or make any simplification over this objective function, again, the hardness is the same as you directly compute the marginal distribution in applying a Bayes rule. So to sidestep this problem, people often try to introduce a simplified structure of Q of Z. Like I can assume Q of Z is fully factorized. It's factorized over each element of Z or each subpartitions of Z, right? That's one way. Or you can assume Q of Z belongs to a simple family of simple distributions like Gaussian distribution or other choices. So doing this is called a global variational inference. Another way is that, okay, I'm gonna relax the objective function itself. For example, I can use convex conjugate to further construct a lower bound of this elbow, like Q of Z, each introducing a set of additional parameters like C. So we expect that in this variational relaxation of this elbow, your optimization with respect to Q of Z, even not putting any constraints, it will be a lot easier. Like the case we discussed in the Bayesian logistic regression, right? And meanwhile, to tighten this bound, right, because you're actually maximizing a lower bound of the elbow here, the objective here, you're gonna optimize this additional variational parameter as well. So this procedure is like, okay, I'm gonna fix this additional variational parameter to C and then obtain an optimal Q of Z, and then fix Q of Z, then obtain an optimal to C. So it's like the YAM procedure. So this is called a local variational inference. And that's the major two approaches we have introduced in our previous lectures. And then we use latent directional allocation as an example to showcase how we conduct the variational inference algorithm, as well as maximizing the elbow with respect to some hyperparameters. Right? So in the last lecture, someone asked nowadays which type of approaches are more commonly used. I would say the first approach, meaning that that is mainly because the progress of the optimization technique. So if we take a look at this elbow again, it is an expectation of approximate posterior Q, right? We take expectation of this log fractional. So nowadays, people find that this objective function is essentially a expectation, right? Expectation under some distribution Q. Right? So if you want to optimize this function, you want to use some gradient. If we denoted this guy as elbow, right? We want to calculate the gradient of elbow over the parameters which determine the Q of Z, right? That's the idea. So, but in many cases, if you make Q of Z to be complex, like what if I just parameterize Q of Z to be a Gaussian distribution, but the mu, the mean, and also the covariance are both parameterized by complicated models like neural network. How do I calculate such an expectation under this Q, right? Not to mention computing the gradient. Yeah, exactly. That's something I'm about to say. Right, this is called stochastic optimization, right? So in many complicated form of Q, right? You can specify a very complicated form of Q, like parameterize your Gaussian posterior, the mean of Gaussian posterior and variance of Gaussian posterior to be a neural network. You are not even able to compute a closed form of this objective function. Right? Not to mention taking the gradient. However, people found that with the popularity of stochastic optimization, we don't care if we can compute the exact gradient of this objective function or the objective function itself. Instead, as long as we can compute an unbiased stochastic estimate of the gradient, that'll be sufficient. If you can view your objective function as an expectation of some random variable, right? Here we can view this log fractional as a random variable. Why? Because it contains Z, right? And the Z obeys this posterior a base of this Q of Z. So this log fractional essentially is a random variable, a function of random variable, still random variable. Right? So to maximize this guy, right, we can try to compute a stochastic estimate of the gradient. So if we take a gradient of this expected random variable, in many cases, suppose your random variable inside is not like very bizarre, you can switch the expectation and the gradient. I mean, you can first take the gradient over this function, and then take expectation. The benefit is that we can just use the gradient inside the expectation to update the parameters. Why? Because for any instance of theta, we take the gradient of this function of theta, essentially is a stochastic estimate or unbiased estimate of the whole objective function. Okay. So as long as you guarantee that your stochastic estimate of the gradient is unbiased, meaning that it takes expectation of the stochastic estimate, it is the original gradient, exact gradient. Then you can use this stochastic gradient to conduct optimization. This is called stochastic gradient descent. But for this case, because we're maximization, so it's called stochastic gradient ascent. Yes, that's a very good point. But we're not going to get to the detail right now because that will when we talk about how to specifically leverage this kind of idea to maximize this elbow directly rather than deriving any relaxation form, we need to make careful transformation. We don't want to our parameter theta depends on Q as well. So that will to do that, we need to leverage a very well-known and very popular trick. It's called the reparameterization trick. This is kind of like standard nowadays. A standard technique applied in any kind of Bayesian neural network inference, or if you want to put the complicated models and you want to do some variational inference, the reparameterization trick is very, it's kind of like a by default trick. By doing so, that means, okay, I can convert this expectation into an irrelevant random variable like epsilon. And then your function, random function, are referred to as a function of epsilon. Then you can freely sample epsilon and then instantiate this function with the sample epsilon, take the gradient. That will be your stochastic estimate of the gradient that is unbiased, and you can use that to update your model parameters. Okay, this is just to give you a kind of like rough idea, and because without any specific model, as an example, it's quite, it will be very abstractive to illustrate those methods. So we're gonna hold on this for a while. When we talk about Bayesian neural networks, and we introduce the application basic ideas of the neural networks, we'll go back to look at how do we conduct variational inference on Bayesian neural networks, and then we'll give the details about how to conduct stochastic optimization in lieu of the reparameterization trick. Does it make sense? Any questions so far? Okay, great. So regarding the latent directional allocation, we expect that you should be able to understand the modeling of latent directional allocation, which is essentially a variant of Gaussian mixture model, right? However, your mixture components now is a categorical distribution. It's kind of discrete distribution rather than Gaussian. And you should be able to derive the variational E step and calculate the gradient for the M step. We mentioned in the last lecture, the computation of the gradient is not hard, but it's a bit tedious. Again, we highly encourage you to follow the slides and to derive those details. It's not hard at all. It's just a good practice of the calculus, and also, you know, all the small mathematical practice problems. And although this is not obligatory, we expect that you are able to implement the LDA inference algorithm based on variational inference framework. Okay. From today, we're gonna discuss another branch of Bayesian inference technique, which is called Markov chain Monte Carlo sampling. For brevity, it is also referred to as mcmc, right? Markov chain Monte Carlo sampling. So I bet the history of mcmc even is longer than machine learning. Before the invention of machine learning, mcmc has already been used in a lot of areas like engineering and scientific design or weather forecast, those kind of stuff. So it was not invented by machine learning researchers. Machine learning researchers just borrow those techniques and highlight their usefulness in our own domain. So we're gonna first give a general ideas of Markov chain Monte Carlo sampling. You'll see that it uses a totally different idea to calculate posterior distribution from the variational inference. And then we'll introduce a simple, but like very widely used Markov chain Monte Carlo sampling. It's called the Metropolis Hastings algorithm. We can view it as kind of like foundation of mcmc algorithms. So nearly all kinds of mcmc algorithm can be viewed as kind of variant or small variant of Metropolis Hastings. Of course, the naive Metropolis Hastings can be quite stupid, honestly, and it's very inefficient. However, if you can smartly construct the transition kernel to generate new proposals, then the Metropolis Hastings can be much more efficient. And we'll talk about the detail later. And then we'll introduce two widely used and powerful mcmc algorithm. Both of them can be viewed as special instances of Metropolis Hastings algorithms. One is called Gibbs sampling. So Gibbs sampling essentially uses the conditional distribution on the conditional Join distribution as the transition kernel to generate the samples. As the result, the acceptance rate is always 1. Right? And the second one is called hybrid Monte Carlo sampling, right? Which is often used in physics simulation. So sometimes it's also called a Hamiltonian Monte Carlo, Hamiltonian dynamics Monte Carlo. So so the idea is to leverage the power of some physical system, which is called a Hamiltonian system. Right? So it uses a dynamic system to to generate trajectory. So at the end of the trajectory, you generate a new proposal. And the benefit is that in theory, if your system is because Hamiltonian system ideally is energy conserving, meaning that your acceptance rate in theory should be 1. However, because you'll never be able to compute exact, you have to use some numerical integration to solve that problem. There is always some kind of numerical error. So, but even doing so, your acceptance rate is pretty high. So that's benefit of a hybrid Monte Carlo sampling. The hybrid Monte Carlo sampling is kind of like a very effective in posterior inference for Bayesian neural network, like a fully connected Bayesian neural network. We have a bunch of experience using hybrid Monte Carlo sampling. It's much better than directional inference, but of course, it's much slower. Okay. So first, let us talk about the general ideas of Markov chain Monte Carlo sampling. Right? So what's the whole idea? Right? Actually, this branch, they follow this big framework, and then different methods just change different components, right? Like what we have discussed in the variational inference. And this branch follow another general idea, and the different methods actually to specify different components as well. Okay? So this is always how we look at how we have the benefit that how we have a unified view of the type approaches. So first, let us look at the goal for mcmc. Right? So suppose we have a probabilistic model. Again, we assume this is a latent random variable z, and you have some prior to sample z, okay? And then given z, you sample the posterior, you sample the observed data d. Okay? And instead of directly computing the true posterior distribution, right? This is a distribution. It's very hard to compute. The goal of Markov chain Monte Carlo sampling is to generate samples from the posterior distribution. Maybe I should use this red marker. How to generate samples from the posterior distribution. So the goal is a little bit different from the variational inference. Remember, variational inference aims to get some analytical form of this true posterior, right? Either, in most cases, just the approximation, right? I can approximate this by some closed form like Gaussian, like mixture Gaussian, or even some complicated form, but it is analytical, right? However, for Markov chain Monte Carlo sampling, we just give up working out any closed form approximation to this posterior. Instead, we just want to generate a bunch of samples from this distribution. So it's like, okay, suppose the God has this ground truth posterior in hand, right? The God can use that posterior to generate the samples. This is what the Markov chain modified sampling aims to do. It doesn't want to calculate this. It wants to just give you samples. That is, we want to generate a bunch of samples Z1 to Zn from the true posterior. That's the goal. However, we don't require Z1, Z2 to Zn are independent. This is something we should be really careful about that. So usually in our machine learning modeling, we assume, okay, this data are collected, they're generated identically distributed and independent, right? But for Markov chain modified sampling, even in the ideal case, you can only guarantee those n samples are identically distributed, but are not independent of each other. Instead, among them have like very strong correlations. So we'll later explain why. So before we introduce the strategy to generate posterior samples, so we would like to highlight what's the usage of the posterior samples. Suppose we have like 100 posterior samples in my hand. What's the usage? Do we lose something as compared with variational inference? In fact, we actually don't lose anything. And actually, it is even more convenient than using variational inference to get an analytical form. Why? We can take a look at this one. So first, although mcmc gives up calculating or approximating a closed form for this true posterior, we can still get some pretty nice approximation of the posterior by using these samples. That means if this is your true posterior to density, oops, sorry. We don't compute any curve to approximate this guy, right? Instead, suppose we are able to collect a bunch of posterior samples for that. We can recover this curve by using some histogram. Right? It's a very commonly used approach. According to, we can bin in this support region, right? This input domain, so we just count how many, the density of the samples in each region. Then I can recover, or at least quite well approximate posterior with these histograms. And there is some kind of basic theorem in statistics. So if you haven't taken that class before, you should have seen that theorem, meaning that if you use samples to approximate the distribution, basically you can approximate any distribution, and it will converge to the true posterior in distribution and with some kind of convergence rate. Actually, we don't need to worry about that. And someone may ask, what if I really want to have some closed form approximation? I want to compute some curve, right, to be close to the true posterior distribution density, right? That's easy as well, because you can use some density estimator, right? I can assume this is a mixture of Gaussian distribution, and I use my samples. I use then I use my mixture Gaussian to fit those samples. Then I can get some curve. It doesn't matter. You just need to adopt an additional step. So that's not an issue for Markov chain modified sample. And the benefit is in the following. Sorry, maybe there's something wrong with this plug. Okay. if you want to estimate some statistics or moments, like if I want to know what is the expectation of this work, right, under the posterior distribution, what's this? I mean, if I want to calculate the expectation of some function of the latent random variable, say z cubic, right? What's the expectation of that? Under this case, even you got some fancy closed form approximation of the posterior, like Q of z to be a Gaussian, right? You can try to compute that. You still cannot get some closed form on that. Right? But with a bunch of posterior samples in hand, you can just approximate. Right? You just evaluate the function at each posterior sample and take an average. Right? This is an unbiased estimate of this expectation, and it converges quite fast, according to the law of large numbers or central limit theory. You see that it converges to the number of samples. And also, it's very easy to compute the predictive distribution. Let me try that. Well, actually, there's no such key in my laptop. Let me just unplug it. Should the batteries it has enough power to last toward the end of this lecture. And if you want to get predictive distribution, it's easy as well, right? You just shove the samples, right? You shove the samples inside this integral, which is a formula to compute the predictive distribution. You get the predictive distribution very easy, right? And even even you can run variational inference, you got analytical form, and if you shove this analytical form approximation of your posterior distribution into the computation of the predictive distribution, in many cases you still won't be able to compute that because you need to involve integration again. What is the delta function there? Yeah. If you want to view it, very rigorously from integral point of view, essentially integral is a delta measure. Right? Delta measure means that you just sum over the instances where the instance as anyway, you just take the derivative of the delta measure and then you do the integral. It's just summation over this samples, and of course the measure over each instance will just be 1 over n. But basically, this is just what we have done many times to estimate something, right? So just like toss a coin, I want to look at what's the chance that your coin you see heads up, right? You just do the average. Right? So any questions so far? I just want to highlight the benefit of the goal of the mcmc. So actually, although variational inference is kind of more popular in large scale data, right? When we do some Bayesian inference, like you want to compute the predictive distribution, want to estimate some interesting statistics or moments, you often need to do the Monte Carlo approximation here again, because you are not able to give some analytical form. So they're gonna generate samples from your variational posterior and do this Monte Carlo approximation. This is very common. So what's the benefit, right? What is the advantage of mcmc? In addition to those benefit to have our posterior samples in hand. First, mcmc guarantees the convergence to the true posterior in an asymptotic sense. So meaning that if you run your sampling procedure for enough long time, it will always converge to the true posterior distribution. So this is unbiased. You can view it as an unbiased approximation to the true posterior distribution. Compared with other approximations like variational inference, as we mentioned before, right? At the beginning, you should either restrict the range of your approximate posterior, or you have to make up some relaxation of the evidence lower bound. So that means there's always a gap between your approximation and the true posterior. So the error is still there. It's always there, no matter how optimal your variational posterior you can obtain. There's still some discrepancy. But Markov chain Monte Carlo sampling doesn't have such a constraint. You just tell, like, if you are patient enough, you can run your Markov chain. Keep running that, and finally, it will end up with the true posterior distribution. The second thing is that it's quite robust to initialization. Meaning that in most algorithms, most mcmc algorithms, no matter how you start with your initial sample, right, you run your chain, it will finally converge to the true posterior. So it's quite insensitive to your initializations. That's very good as well. Otherwise, especially like in neural network-based applications, how to initialize your model parameters becomes an art. People have summarized a bunch of different techniques to do the initialization. And there's a bunch of machine learning topics called meta learning, which is specifically designed to how to learn the good initializations for the neural networks to do something. It's called meta learning. Right? And third advantage of mcmc is that the empirically works best, and often use the gold standard to test the performance of other approximate inference algorithms. Like if I invented a new variational inference algorithm, how do I know my new variational inference algorithm gives better quality? People will usually, okay, I'm gonna first run a Markov chain Monte Carlo sampling, like for 3 days or for 10 days to get my approximate posterior, and look at if your variational inference can get the posterior closer to the posterior obtained by the mcmc. It's not like reverse. Like people won't, like if I develop a new sampling method, people won't evaluate based on some variational inference result. That's kind of like a agreement in this community that people found. People usually use Markov chain Monte Carlo sampling as some kind of gold standard to evaluate the quality of your posterior inference. And indeed, it's true. We've got some work in Bayesian optimization stuff. So basically, Bayesian optimization is to maximize some unknown, some functions, some black box function, meaning that you don't have any closed form of function. You don't know that form. You can only query the value of function at different inputs. So you want to maximize the function. Right? Bayesian optimization basically use some probabilistic model to approximate that function. Then leverage the uncertainty or the posterior distribution of your learning results to decide and next step which input to query, right? And then we expect that after query more and more, you're kind of get closer and closer to the maximum of that function. So the very important step in that is that if you want to query new inputs, you want to optimize some so-called acquisition function to evaluate which inputs is better. But that acquisition function is based upon the posterior distribution of your current learning result. And we found that indeed, if you use Markov chain Monte Carlo sampling, like hybrid Monte Carlo, it is better than using variational inference. This is kind of indirect proof that your posterior inference quality of mcmc is better. And of course, there are some kind of many toy cases where you can just compare the learned posterior distribution from the variation inference and from Markov chain Monte Carlo sampling, you see the difference, and the uncertainty, especially the posterior variance estimated by mcmc, is usually more reasonable than those estimated by variation inference. And the last advantage comes from the previous analysis you just did. Samples are more convenient to use than approximate distributions. Again, if you want to compute the expectation for some moments, which is a complex function of your random variable, and using posterior samples is very easy. You just evaluate the function at different samples and do the average, or the calculation of the predicted distribution is very easy. Of course, there's no free lunch. What are the disadvantages of Markov chain Monte Carlo sample? The most, I think, the most severe problem of mcmc is that it is too slow. It is really orders of magnitude slower than variation inference or variation base. And the major reason, from my perspective, is the so-called random walk behavior. We'll talk about that later. But basically says that many Markov chain Monte Carlo samplings, many of your generated proposals or samples are rejected, meaning that you are doing nothing. You spend a lot of cost in generating those potential samples, but they're rejected. They're not valid. So you waste a lot of computational costs. The second thing is that although mcmc guarantees asymptotic convergence, right, in the limit, you don't know when it really converges. So you know, okay, as long as I go along that direction, I can always get the north pole, right? Sorry, is this north direction? Maybe I just point the wrong direction, but just to give you a sense, right? I know that as long as I go that way, I can arrive at north pole, right? Oh, actually, it's arbitrary direction can give you the north pole. I don't know, anyway. But how long, right, will you arrive at that destination place? We don't know. That's the major issue of mcmc. I need, in many cases, we need to estimate how fast it's gonna converge, right? But it's hard. And even you don't know, you cannot guarantee at the current stage if your chain has already arrived at true posterior or not. There are a bunch of heuristics, like you can look at the trace plots, like you can look at the trajectory of your samples, and if they become stable, not like perturbating a lot, then that may be a good sign, but there's no guarantee on that. So that's something annoying, right? For good chains, it can converge fast, but for bad chains, it converges forever. You can run forever until convergence, meaning that you might need 100 years to converge. It's not meaningful at all. The third disadvantage is hard for parallelization. And you see that Markov chain Monte Carlo sampling essentially is to generate new samples through a Markov chain. So you need to condition on the current sample, the previous generated samples, there are new samples. So it is sequential in nature. It's very hard to get parallel samples. If you can do the parallel, then even you can run a long time. We might be able to accept that because you can distribute the computational cost, right, to make it in parallel. However, because the sequential sampling nature, it usually cannot be done in parallel. Right? And so hard for large scale applications. The reason is also simple because if you want to check a new sample proposal is valid or not, you have to evaluate the joint distribution over the data. If the data is large, this evaluation is very costly. Right? So this is to generate one sample. Right? Remember, if you want to make your chain to converge, you might generate like tens of millions of samples, right? You have to evaluate the likelihood of the data, the log joint probability for million times. That's really, really costly. And finally, it easily trap into single modes. So this is the same as variational inference. So basically, if your true posterior has multiple modes, means that it has multiple higher density regions. Right? So if you run variational inference, if you start here, it might soon converge here. It will give you something like that. As your approximate distribution, it will just ignore the other two modes. And mcmc, although in theory, can discover all the modes, meaning that in theory, after you run it for 100 years, it might give you a good approximation of all the three modes. However, once it generates samples and found high density regions in one region, in one mode, like here, it's very hard for mcmc to jump out this region and to explore new region of new high density regions. That's an issue. And now, although in theory it can, but there are some like theoretical analysis showing that okay, it might take an exponential level of number of steps to jump to a new region, which is basically saying in practical, it won't be able to jump out. So how to scale up Markov chain Monte Carlo sampling to big data is a hot research topic. So basically, we give a kind of like a better and comprehensive overview of this type of approaches to tell you, okay, this is good in some aspects and this is bad in some other aspects. There's no free lunch. Okay? And as to whether you're gonna use mcmc or variational inference, it totally depends on your application. Okay, so now we're gonna illustrate what's the basic framework for mcmc. So the basic framework of mcmc is to construct a Markov chain. So how many of you have heard of Markov chain? Okay, great. So basically, our Markov chain is you can view like a probabilistic model which generates a sequence of variables. So you can denote this sequence by Z1, Z2, Z3, Zn. The significant property of Markov chain is that you generate the n+1 variable, which we denote by Zn+1, conditional on all previous variables. This is only determined by the most recent variable. So that means the conditional probability of state at n+1 conditional on all the history states is only determined by the most recent state. This is called a Markov property. It doesn't account for long dependency. It only determines it is only determined by the state from the last step. So mcmc will construct such a Markov chain. And this chain guarantees that if you use this chain to generate new samples, that means new states, right? In the limit, the marginal distribution of the state will converge to the true posterior distribution of the Z, the random variable, conditional on the data or given the data. That's the idea. So the key is how to construct such a chain. Once you construct chain, what you do is just run sampling procedure, right? You construct your sample chain is very easy, right? You just give an initial distribution, right, to sample Z1, right? And giving Z1 to sample Z2, from this condition distribution, right? Given Z2 sample Z3, keep doing that. That's it. So the key is how to construct this conditional distribution to generate the next sample. And again, to guarantee you finally converge the true posterior, of course, this conditional distribution in mcmc literature is also called the transition kernel. Must embed some knowledge of your drawing distribution, right? Otherwise, how could it be possible to converge to the true posterior distribution? And also from the sampling procedure, because each state, like Zn, is sampled given Zn minus 1, right? And Zn plus 1 is sampled given Zn. Right? So the generation of each state is highly dependent on the state in the previous step. That's why those samples, Z1, Z2, Zn, Zn plus 1, Zn plus 2, they are strongly correlated. And even your chain converges to the true posterior, the marginal distribution of each Zn in the limit follows the true posterior. But Z and Zn plus 1, between them still have strong correlations. You can now view them as like independent samples. And to reduce the correlations, people usually like collect samples every few steps, like you collect posterior samples every 10 steps, like Z1 and Z11 and Z21, 31, something like that to reduce correlations, but still there are some kind of correlations there. So given any Markov chain, right, the whole distribution of the chain is determined by two things. First, the distribution of the initial state. Right? If it is from a Gaussian distribution with mean 0 and covariance 1, it might be different from another distribution, initial distribution like a student T distribution. Right? However, in Markov chain multi-pattern sampling, we do not care about it too much. Why? Because we want our chain to be robust in the sense that no matter how I choose the initial prior of the initial state, it will converge to the same distribution, which is the true posterior distribution. And the second component of a Markov chain, which determines the chain's behavior, is the so-called transition kernel. That is conditioned on the current state, how to sample or generate the next state. So in their literature, they usually use this T to represent transition. Right? It represents how you starting from states, your state start from Zn to Zn plus 1, which is essentially a conditional probability distribution. And the property of Markov chain is largely determined by the transition kernel. For example, how fast it converges to your target distribution. If this transition kernel is the same for all n, meaning that it doesn't change, the form of the transition kernel doesn't change along with the step n, then the chain is called homogeneous. If it's inhomogeneous, means that this T is also determined by the current step. So, in a nutshell, the development of a Markov chain multi-color sampling is the art to design the transition kernel. And you see different types of Markov chain multi-color sampling just to give you different type of transition kernel. Okay, any questions so far? I do not care means that I don't want this distribution of the initial state influence the final stage. That's the goal, right? Because we want our chain to converge to the true posterior, right? Whatever, starting from whatever distribution. That's our goal. But that does not mean like every chain will satisfy that. This is not. You have to make sure your chain satisfies some property to ensure it is invariant to the initial states distribution. You cannot. Like if you take infinity, how can you say that in practice you have arrived at n equals to infinity, right? In practice, you can always say, okay, maybe I take n to be 1 million or 1 billion, right? That's the most, right? You cannot run for infinity. That's the problem, right? The theory tells you, okay, when n goes to infinity, it converges the true posterior for sure. But practice that you cannot run your chain for an infinite amount of time. Right? You can run a large time. At that stage, we believe that it either has already converged or the distribution of the state is very close to the true posterior. However, in most cases, there's no guarantee on that. It's totally based upon the empirical experience. For some data, for some task, for some chain, it converges faster. But sometimes it doesn't converge. But there's some like practical trick to practical heuristics, like looking at the tracing plot to see if it is likely to converge. And it's just likely to converge. It's not saying, okay, if I look at this plot, it's stable, it guarantees converge. There's no guarantee on that. What? It's also determined by users. You mean how many samples do you need to approximate anything you want? It really depends. I mean, like a common choice is just 100. That'll be enough, and your accuracy will be 0.01-ish. Like if you use 1,000, it will be even better. But it's usually people won't use that many. Other question? Yeah. Yeah, that's something we're gonna look into the detail. Actually, different algorithm will have different design of the transition curve. The simplest one maybe just the symmetric Gaussian. Like given Zn plus 1, given Zn, your Zn plus 1 is sampled from Gaussian with mean Zn and some variance. That's the simplest one. But you have other methods. No. Actually, we're going to discuss in 1 minute. So it's about you have to specify 2 stages. One is called burn-in. Before burn-in, you just run throughout those samples. But after burn-in is at the stage which we believe we can collect the samples. Then you need to store samples. Other question? Okay, so we just look at the basic property of chains, right? We would like to know if a Markov chain converges. Remember, some kind of chains might not converge. So suppose this chain converges, right? What kind of distribution it will converge to? So this distribution that the particular chain converges to is called the invariant distribution. What does it mean? It means that, okay, if my distribution of the state, the current step, is here, right? And then after some transition, I got next state. that state is gonna follow the same distribution. This is called an invariant distribution. If that distribution, and that distribution is where this MC converges to. If you look at the definition here, if we're more clear. So if we denote the invariant distribution by P star, so we see MC converges to P star just means if Z star is the current state, is sampled from P star, and then following some transition kernel, which is a conditional distribution that defines your chain to generate a new state Z or new sample. And the marginal distribution of this new sample Z will follow P star as well. Then P star is called the invariant distribution. Does it make sense? That means, okay, suppose you're at current stage, your state of the chain follows some distribution, right? And then you apply some transition kernel, you get a new state. The new state follows same distribution. And you can imagine, like, given this new state, you generate a next state. The next state will still follow the same distribution. So the state distribution now becomes stable or invariant. That's called the invariant distribution. So if there is such distribution P star, which is invariant to the transition kernel, then we call P star as the stationary distribution for this chain. Okay. You're asking we're now using the data everywhere. We're using it. Yeah, as we mentioned, it will be encoded in the transition kernel. That is the design of your transition kernel must have the data information. Otherwise, how do you must have some information in the data, right? Otherwise, how do you make your chain to convert to the posterior distribution given the data? So obviously, we want to design a transition kernel to which the target posterior is invariant, meaning that we want this P star is the posterior distribution of Z given data. Okay? And then the problem is how to design such a transition kernel. So to design a transition kernel, like if the true posterior is invariant to that transition kernel, we need to examine if it's indeed invariance, right? So following the original definition, right, the naive definition, what is intuitive, but it's not very easy to verify, right? If Z is kind of high dimensional sample, right? This integral is again hard to compute. Right? So people comes out with different ways to examine invariance. So like this, most commonly used way to check if your design transition kernel, your true posterior is invariant, to which the true posterior is invariant. Right? This condition is called a detail balance, but this is just a sufficient condition. It's not a necessary condition. Meaning that there could be some invariant. The T could be there could be some transition kernel T, P star Z is invariant too, but doesn't satisfy detail balance. But because it's so convenient, so people most often just use a detail balance to check to ensure that your design transition kernel is something what we want. Okay. So what is detail balance? Detail balance just says if for arbitrary two state or two state values, Z and Z prime, if you evaluate Z with the true posterior P star, and then multiply the conditional probability to sample Z prime given Z. So basically, it's just a construct drawn probability, right? You first sample Z from the true posterior, and then sample Z prime from the transition kernel. It's the same as you do this reversely. That is, you first sample Z prime with the true posterior, and then sample Z conditional Z prime, meaning from the transition kernel. These two joint probability density is the same. Then we call T the transition kernel satisfied detail balance. Then you can safely use T. Because if you evolve your chain with this T, guarantees to converge to this target posterior. So intuitively, you can explain like detail balance just says, okay, you first use your target posterior to sample Z, and then use your transition to get your new sample Z prime. This whole probability is the same as you first sample Z prime with your target posterior, and then use your transition kernel to sample Z. You can jump out and then jump back with the same probability. So why checking detail balance is convenient? Looks like if this is a true posterior, right, we're not able to evaluate true posterior. If we are able to evaluate true posterior, why should we calculate true posterior? But here, there's benefit. We actually don't need to shove the true posterior here. Why? Because the true posterior is always proportional to the joint distribution, right? So if you represent the true posterior in terms of the joint distribution, so you can substitute for the joint distribution divided by the marginal distribution of data for the true posterior in both sides. What can we observe? Yeah, P of D, the marginal distribution of data is cancelled. You actually never need to calculate the true posterior. You just need to verify if the joint distribution of your sample Z along with the data multiplying the transition kernel to generate Z prime is the same as the joint distribution of Z, Z prime multiplying with the transition kernel from Z prime to Z is the same, which is equivalent to concluding the transition kernel is invariant to the posterior, the true posterior, because they only have they essentially just multiply a factor, same factor on both sides. Does it make sense? Okay. So here we want to do a simple practice to show why detail balance can lead to invariance. But again, I want to emphasize that this is sufficient condition. So you can use that to check if your transition kernel satisfy this. Okay, it guarantees to converge to P of star. However, it does not mean if T doesn't satisfy this, it is not invariant to the P star is not invariant to T. There's no guarantee, but in practice, right, this is just for convenience. I just want to give a quick test of my T. Right? Even I have some like error. This is acceptable. So let us try to show why detail balance can lead to invariance. So remember the definition of invariance is that if you start from Z, right? If you sample Z from your target posterior, then your conditional Z to generate Z prime. If you look at, so this guy is actually the joint distribution of Z and Z prime, right? If you look at the marginal distribution Z prime, that means you have to marginalize out Z. This marginal distribution should be the same. It's still the P prime, right? So if the detail balance is satisfied, let us see how this marginalization will lead to this, right? So we can look at it because the detail balance says P star Z times the transition from Z to Z prime is equal to P star Z prime and transition from Z prime to Z, right? So we just apply the detail balance results. We just replace Z by switch Z and Z prime. So you get P star Z prime, and Z prime goes to Z and DZ, right? So this guy is equal to this guy according to the detail balance. But now the integral is still with respect to Z. Now if you can take a look, this transition kernel essentially is a conditional probability of Z given Z prime, right? And the Z prime is not integral variable, right? You can move it out. So it's just a P prime, P star Z prime times PZ gives Z prime and DZ, the set. Yeah, it's this, right? So it's very simple proof, which can show why detail balance can lead to invariance. So if you can construct such a Markov chain, so whose stationary distribution and the transition kernel respect the detail balance, then this Markov chain is called reversible. I mean, this is just the concept. You don't need to memorize that. If I'm taking any like ECE class before, they're gonna spend a lot of time talking about Markov chains. They're gonna introduce like tens of terms or hundreds of jargons and talk about all kinds of properties of the Markov chains, like aperiodic, like irreducible, reducibility, and all kinds of stuff. And ergodicity and all kinds of stuff. Is hard to memorize all of them. But here we just want to point out the key concepts here. Okay. A Markov chain can have multiple station distributions. That's why we mentioned that we don't want to our initial states distribution influence the final distribution the chain converges to, right? So, however, if you don't restrict a Markov chain, you can construct a Markov chain which can converge to different stationary distributions, and it depends on the initial state distribution. It's like you might chop here, you might chop here, you might chop here, you might chop here. And this is not what we want. We want our Markov chain only converges to the desired posterior, no matter what initial distribution is chosen. That's our goal. If you can construct such a Markov chain, right, it only converges to one stationary distribution. This chain is called ergodic, and this property is called ergodicity. So ergodic Markov chain only converges to one invariant distribution and one stationary distribution. So informally, for ergodic chain, the chain has the positive probability to go from every state to every state. So basically, if this is your state space, meaning that all possible values of your random variable can be taken, the ergodic chain means that okay, it is possible to jump to every possible value in this domain. However, if it is not ergodic, meaning that it is reducible, meaning that it might converge to one station distribution here, another station distribution here, and it's often the case that there is some chance you jump to here and then never jump out. So if I'm taking, again, a Markov chain model, the ECE class before, you should have learned that case, that is some kind of a rigorous definition. It's called the jumping back probability. If the state jumps from here and to another place and jump back, no matter how many steps it take, this probability, this total probability is still zero. That means it's not jump back, and then your chain is not then your chain is not ergodic, and is likely to converge to different station distributions. So ergodic chain is also called irreducible. But anyway, those words are not useless. Is useless at all. Just give you some name. So if we have an ergodic chain, and then the invariant distribution or station distribution it converges to is also called equilibrium distribution. So those are kind of like confusing words used here and there, but every time we say, okay, this chain has arrived at equilibrium distribution, it's basically it converges to the station distribution or invariant distribution, whatever.
So what's the exact definition of
Yes, the informal definition. The formal definition I cannot give you here because I cannot recite it as well. But basically, it is defined based on the jumping back probability. Like this is your state space, right? If this is your S might belongs to Rn or might be in discrete space. It just tell you if what is for any state Si say Zn equals to Sj given Z. Let me write it in this way. Given the Zn to some state and Zn plus k to another state, Zi, okay, what's this probability? It's possible that if you sum over k from 1 to infinity, this guy is still 0. And in that case, it is not irreducible.
In the case of this group,
not too much difference conceptually, because people when they introduce this ergodic or not ergodic, they usually use the examples of discrete state space, but they can also be defined on continuous state space. Yeah. Actually, if you have discrete space, you can try to draw a graph between the state space to ensure that, like, if you have a state here, that means okay, at some step you got this state, and it just means through some finite number of steps you have positive probability to reach this step. However, if you can show that for finite steps, you take this step, jump to this step, the probability is 0, then there's no connection, and then it's not irreducible. But anyway, this is not like a class talking about Markov chain because it's a big topic. If you're interested in looking at all these properties, you can take a look at, and also what is periodicity of the chain, right? And what is aperiodic, it's basically the common factorial number of the number of steps from one state jump back to another state. If it's bigger than 1, it's periodic. If it's periodic, it's not irreducible as well. Now here we want to emphasize that basically when you develop Markov chain Monte Carlo sampling, we look at literature. when people are talking about, okay, it converges to stationary distribution, it arrives at equilibrium distribution, or you got the invariant distribution, is the same thing. It just means that your chain converges. Don't get confused about those terms. So in Markov chain Monte-Carlo sampling procedure, right? We need to guarantee. We actually have two guarantees, right? To ensure your sampling procedure is valid. First, you must show that your true posterior is invariant to the transition kernel. That will guarantee the samples will converge to the true posterior. This is called unbiased. The second is called ergodicity. So the ergodicity guarantees your sample space can be fully explored rather than partially explored. So that basically means if you have like 2 moles, and ergodicity guarantees that, although in practice it's very hard, your samples will go through all the whole real lines, and so that they can capture the 2 moles here. And however, if your chain doesn't satisfy the ergodicity, it is possible that it only generates samples along this region. It will never generate samples in this region, in another input region for the second mode. So, however, ergodicity is not very hard to guarantee. It can show that a homogeneous Markov chain will be ergodic, subject only to weak restrictions on the invariant distribution and transition kernels. So in most cases, I can just by default assume that your chain is ergodic. Again, the key is to design the transition kernel itself. Oh, okay. Sorry, again, we are running again a little bit late. Okay, so let us continue on Thursday.